asking, where are we? Where are we? And the EIB, Enterprise Breeding System. So now we have Tom and Kate to let us know where we are and where we're going to be.
Hello, can everyone hear me okay? And hopefully I won't be a distraction, but I'm the kind of person that has to walk back and forth, so I will be myself. So I think for today's seminar, this is the first time I've met many of you. Some of you I've worked closely with, some of you for the first time. And so I asked myself and Kate, what should we talk about? Well, there is, what is the objective of this system? So there's a fair amount of breeding or scientific rationale behind it. And then, of course, to enable that, there's the IT. And so the science of this, the IT of this, and specifically how we're creating the system, where we're at, and where we envision being by the end of the year and into next year. And so I just kind of quoted, from some of the EIB documents, at a high level, these are the goals of excellence in breeding. We talk about modernizing breeding programs. What are the practices that it takes to do these things? And that, of course, are must-dos for the IT capacities of the breeding system. And we have created what I call the excellence in breeding architecture, as this is a planning diagram to help us understand what are the capacities, IT capacities, that a breeding program needs to execute not only the breeding practices of today, but as they go forward, the breeding practices as they modernize. It needs to be the same IT. And so we use this to plan, what type of capacities are needed, and to isolate them to different modules or boxes on this diagram so that we can concentrate our efforts in appropriate ways. And the creation of this is not necessarily going to be just the EBS. Other teams will contribute to this, the GOBI team, the BMS team, the BRAPI team. So this is a way for us to understand how our work comes together to create the IT capacities for modernized breeding. And to help us direct at a strategic level our work, we've formed a steering team, and of course, as new partners come into the project, there'll be new members and some will go off, but this team is how we identify what, appropriate alignment between different stakeholders and key objectives. And so from this, we've defined, well, who are we addressing? And so the goal for this year is to create, since we're standing up the first version of the system, the core logic of that system, and then in next year start working with CIMMYT, maize, wheat, IRRI, rice for systematic adoption, and that won't end next year, will continue. My experience is that adoption at a minimum takes a good 3 years. We'll very much start that in those types of activities to get systematic adoption of those 3 crop breeding programs, but start planning for the expansion, through the CIMMYT Maize and Wheat Gates Foundation Renewal Grant. We've identified, a CARTA for wheat and associated NARS, IITA for maize and associated NARS. Rice at IRRI has similar things. And so we'll engage those groups starting this year to start a planning process for how they start coming into this. And again, this is going to be a collective response. The EBS will not do all of this. Some of the work will be by other IT partners. Some of the work will be done by the breeding programs themselves. And so we're following this model here, that as the EIB engages to modernize, and that exists specifically as what's called an EIB improvement plan, where you've identified, there's been what's called a breeding program assessment, a BPAT, and we've done a review of that program and identified strengths and weaknesses. Then excellence in breeding engages to how then do you propose to address those? And the funding for that then is manifest in, for instance, the renewal grant of CIMMYT, maize, and wheat. And we, in turn, have funding from the Gates Foundation flowing through Excellence in Breeding. And our role is to focus on, as an EBS team, the building of it and the deploying of it. There are then what are called adoption activities to work to get it into the hands of breeders, and we'll come to that a little bit more later. And then, of course, once it's deployed, we will deploy this as a multi-tenanted software as service. But and so, of course, how that is kept operational. But there will also be, as appropriate at different centers, on-premise things. That their gene bank may be on-premise, but we want to connect that to, like here, the maize, wheat, Grin Global to the EBS. They may have local analytical labs, so there'll be a mixture of this, and so there'll be a mixed support environment. Now, getting a little bit to these types of adoptions, that one element of, this is from B4R, is that the ability to configure it, not only through what widgets you see when you first come to the opening dashboard. So if you're, in pre-breeding and you're focusing on sampling and genomic selection type work, or if you're a field operation person focusing on planting and phenotyping, that what you see, so the different types of tools and capacities of the EBS, you can just come straight to them. The other way is that this is a metadata-driven system. We have to create logic that's crop agnostic, procedure agnostic, but it's how that logic specifically behaves is driven by the metadata defining, I am this program, I am this product profile, I am this stage of my schema, I am doing this type of operation. And so there's that element, that is data that has to, of course, be defined and loaded to the system to have the system behave in an appropriate way for that specific crop breeding program. And, kind of go over these. And so at a higher level, these adoption or configuration activities, that I was, from Kate, we had some screenshots of that configurable portal. That is not only what you see, which could be saved, but also the metadata of it. And that is an example then of these configurable applications, again, which are, the metadata for that. But there's what we're calling authentication logic that when, this is a system service, but when you log on, who you are, your roles and responsibilities. So of course, we have to have access to that data. There's what I'll call process logic. Again, this is not only a sequence of software behaviors based on the metadata of that program, but also in some sense, when you create a trial, or you create an analysis request, or you create a genotyping request, you're creating a set of instructions that, that can be handed along. And then the things that ties the different elements of the EBS together will be a service gateway that enables appropriate APIs and other means of data exchange. And then, of course, there are other foundational modules which for breeding exist in B4R, your experiment creation, your seed inventory management. These are singular because you don't want, if you multiply them, not only is that very inefficient in software development and support, but you're fragmenting your data, which makes it very challenging to bring together data in the right way for analytics and decision support and things like that. But then there are what we're calling frameworks, and I'll go into that a little bit later on, but this is where you have common logic enabling many, many different types of statistical models. There's also what we're calling connectors or containers. For instance, with drone imaging, we're not going to build the image processing pipeline for managing drone images and extracting signals or traits, but we can build to that edge because they need breeding trial data to understand, here's this plot, what's in there, so they can align their images to that. Or in the same way with envirotyping, soil, weather, whatnot, farm management data collection. We'll build to that where that information is available, but we won't build that software or technology per se, but they can connect to us to consume that data and according to that give back data. But also, we're not going to do everything, and so there are things that are meant to be part of the EBS, so we can make sure they're very tightly, efficiently integrated. But then there are things that will be more external, such as Grin Global here. It can connect to us, have appropriate exchange of information, but it's not formally part of the EBS. So for beginning of this year, as we were, starting from last year and more formally beginning of this year, with our steering team and the early adopting, readers, we said, well, what must we do this year? And so these are our objectives for the year. The ability to, we will create this concept of a minimum viable implementation of functionality for doing, these seven activities. But also, right now, we're sort of on our own development schedule, but we know there are different breeding cycles. And it may be great, for instance, that we create some type of analysis capacity in November, but if the breeders need to use it in April, that means they're out of sync, and it'll be, even though we've delivered it, they won't really use it for a whole nother year. I mean, so how we start better aligning, our sequence with breeding sequences. So that will be another goal, going into 2020. And what is the minimum viable implementation? That there's a lot of complexity here. Like I said, we have to be crop agnostic, procedure agnostic. We have to support not only current practice, but future state practice. And even if we try to constrain it to just maize, wheat, rice, that the breeding organizations at CIMMYT, IRRI, given the importance of those crops and the scale then of activities globally, these are excellent use cases for the complexity we face, to do this. And so even though there's a lot of expertise in the breeding programs and on the IT team, we can get it wrong. So the idea of a minimum viable implementation is that this is our best understanding of the correct logic, not only in terms of, what people do, but our understanding of data models and technical architectures and things like that. So get that out there and ask if it's correct. And if it's not correct, we can change it. But if it is correct, then you start that cycle of every development period. What are the key prioritized enhancements? And you work, towards that. So this year, again, the goal is to create this core logic of the system, that prior slide, those 7 objectives. And next year, then, from this, as we work towards full adoption by these breeding programs, that's where you start having these cycles of enhancements being added. Now, to do this, we've had to formulate an IT team, and I really want to, call out, Kate and Marco and Ernesto, Arjun, Victor, the various members. We work together to say, if this is what we're trying to accomplish, this is technically what an enterprise breeding system is. These are the types of competencies we need on the IT team. This is how we envision functioning as a blended team. And so I really want to acknowledge, the efforts that Marco, Kate, Ernesto, others took to really do this and identify this. And I have a lot of confidence in them and the team they've recruited, to do this work. And so this is not only how we're organized, but also roughly a classification of the types of competencies that are needed to do this type of effort. And CIMMYT is also helping with, that given the, unfortunately I've learned there's a lot of complexity here about legals and finances and whatnot. So CIMMYT is funding a person to help us, manage all that. And this is the breeding advisory team. We've identified, Terry Molnar is the overall product owner. In some sense, Josh is that also at IRRI. And Prasanna has identified, these individuals to focus with us this year, and Hans, these individuals. And again, also part of the thinking is, even though both these crops are global, start with, focus a little bit more on the work that's done here, because we can go find them and talk to them, and we can talk to each other. It's much easier as you're getting started. But certainly with an eye towards, this has to scale not only to all CIMMYT or IRRI operations, but again, eventually other partners. Another key role that we've created, and Kate, I don't know if you want to talk to this slide or like me to do that, if you have a preference, either way. Starting with, there is a transition occurring. The data management group has worked, very creatively and competently to keep things running in the absence of breeding informatics. But of course that doesn't scale, and as the scale of operations and the pressure, to modernize and intensify is going on, it's not sustainable. So how do we transition to software doing that? And again, this role of research requirement analyst, they have the subject matter expertise, so they can sit down with a breeder, sit down with a genomic scientist, sit down with a statistician, and understand what you're doing, but in turn, translate that to the IT people. So you have two worlds focusing on their expertise. And again, in modern science, the pressure is to ever more focus on that. So this person who can bridge between them is critical. And so starting with Kate and some other members of the team, they're now about half time on this project this year. So they have the ability to focus on this role. And it's not just people here. So for instance, from module 3, high throughput genotyping project, we have Milka, to help understand a little bit broader context, because one EIB goal is to standardize genotyping so we can bundle up all the samples and get better price points and efficiencies on that. And we had a meeting, and part of our practice this year to get this going is that we're having episodic, about every 2 months, a 2-month session. We're bringing together individuals to really not only, according to our objectives, define, of course, meet each other, familiarize themselves with each other, understand, obviously, like for instance, IRRI, it's plus 13 hours. Well, you have to do a lot of email stuff, and so it's easy to miscommunicate when you have this continuous communication. So you've, gotten to know each other, but also developed the methods for how we do this, but then do it, do an example of it in those 2-week sessions. And coming up, we're going to have one on what's called DevOps, and another one on, the service gateway layer. So we'll be having episodic meetings of this nature to really help make this happen. So to kind of get back to our key objectives, if you kind of put this out as a cartoon, the ability to create experiments, that's B for R. Ability to do analytical sampling, that's sample manager. The ability to analyze them, that's like frameworks. So these are the elements of the system that we're going to be touching. And this is our planning portfolio for the year. And there's a couple things here. These are ones that are most crucial to that core starting minimum viable implementation. And that very first EIB diagram just kind of mapped it to those high-level modules. You can see what we're touching. And between the EBS team, who's doing what, so this, of course, is IRRI members of the EBS team, because this is in B4R. This here is the CIMMYT team, and so we kind of looked at what is where in the system, or what should be where in the system, and what kind of makes sense in terms of where that team member is situated to do that work. But we're also contracting with DART to work on KDX, and we do have to have a relationship with KSU for the KSU Pheno apps on their handheld. But you can see that in quarter one, last year we had a very, very small team. We could only really do a few things at a time. And so with the increased funding, as you saw in that prior slide, we were able to increase the team, and we then in quarter two, started scaling, from that 2-week meeting and in prior planning meetings, we defined these projects and the goal of conducting them, completing them in June, and I think on the whole that's what's happened. Of course, given this is the first time, there's also lessons learned, and so part of this is how we get better at doing this.
What do those numbers stand for after B?
Excuse me?
What do those numbers stand for after B?
Okay, so those are, I guess I was using phase one, so that for the breeding experiment creation tool, we have the third version of it, I'll say. Maybe I should change it to V. But you can see many of these are at phase one, and again, according to our concept of minimal viable implementation and also the concept of a maximum 1 month development period. Now in that, part of that is actually code writing, part of that's testing, part of that is verification, but that's the maximum. So in a 1 month period, that's the unit of work for these different elements that's being conducted. And I also want to mention that at the end of this there is a release. Now sometimes it's very foundational. It is not useful per se to an end user, but it built some maybe core database functionality that then the second version would then start adding user functionality on top of. So it's not uncommon that we'll have a couple hops of these projects. And our goal is to have by the end of this year, and given that there's January, vacations or whatnot, and in December, to me that means say mid-January 2020, we'll have what we're calling the first version of the EBS proper, where through the work of these different tracks on these different elements of EBS, they will come together as a functioning EBS. But it doesn't mean, though, that particularly with B4R, we envision that can be deployed independently. So for instance, you could start doing things in breeding trial experiment creation for, well, it's being done already at IRRI. Here, we're dependent on associated data migration and some of these configuration activities defining metadata. But I would certainly say in quarter three, that a breeder could actually go there, use that tool to create a trial. Now it would come out as an Excel data file, but they could still do that. So depending on if the part is meant to be independent, it of course can be used independently, and it has in some sense its release schedule for that. But other elements are meant to be parts of the system, and so they're dependent on that system release. Or another way of saying it, even if B4R is there, it won't have this, and so if you really want to analyze those trials, then it has to be connected to the EBS along with the analytics framework. So just as a cartoon, of how we do this, starting with high-level objectives down to, this team is working on one of those P numbers in that period of time. And, so you have projects that kind of build to this concept of, starting minimum viable implementation, and you keep going, towards more your full, complete definition of the system, and you have these different activities, the design, the development, deployment, adoption activities. So this tries to capture, the practice and process, that we go through. So getting back a little bit to science, the EIB is working with breeding programs to define a product profile. Those have defined, traits or characteristics. Some of them are genetic characteristics. Some of them are more human characteristics in terms of, that people prefer, having this type of maize variety over that type of maize variety. Sometimes there occur social traits or gender traits, well, as we think, and I would agree that they're not genetic based. But anyway, either way, that that a breeding trial is measuring their performance and also acceptance criteria. So we want to be able to design trials to collect the necessary data, conduct the analysis to ask, which ones met or attained those acceptance criteria, and of course have the decision support for bringing that data together to make these decisions. And the other thing that we have to really do is that, there will be this concept of a breeding pipeline or schema, and they may not be done by the same team per se, and it may not be done by the same center or organization per se, but we have to enable, the operations for these things, but also the operational connection, data connection between them, so that as you go from, say, more like what Terry's doing here in sort of this identifying appropriate varieties that come into core breeding, and then like for week, this would be a lot of what happens at Obregon, and then of course you're passing it off to your national partners for that more lighter scale testing and validation, and then of course it ends up on the farm, and you want to be capturing, well, what was the adoption? How well did we really succeed in delivering to them, not only this bag of seeds, but the G by E by M understandings they can use to understand which ones they should use and how they should manage them in doing this. And the other key thing is understanding where our error is. If we're going to increase genetic gain through more rapid cycle time, selection intensity, we have to become more predictable. That an outcome of and predictability means that the outcome of a trial, if I did the same thing again in the future, that same state, G by E by M, it would behave similarly. If it doesn't, then that trial is really just a one-off experience, and we might as well have not done it, because it doesn't really allow, you have to do many, many more of them. It's very inefficient. You have a much higher failure rate and much longer period of time, and the success on the farm is much less. So how do we become more predictable? So we have to understand, well, obviously improve practices, have a clear definition of that product, have improved according to your breeding pipeline at that stage. What's the objective of that trial, the appropriate design of that trial, and the best practices of executing that. The analytics to capture out, the signal from the noise and understand that. And so at the end of the day, you're working to reduce error so that, you want these arrows to be flipped. Okay, because if you don't do that, if you take into account your error, your eye may fixate on, oh yeah, if you look at that prior graph, accept, reject, and you say, oh yeah, look, this one's better than this one. Well, no, it's not. Okay, if you redid this again, these things could totally change order. You're not taking into account error. So it starts with experiments. That is the starting point, not only in terms of an operational unit, but defining the data from which everything else happens. And so that's one reason why we're investing so much in that in B4R, that logic, and centralizing that. We can't allow experiments to be created anywhere, because it just creates a nightmare with data integration and operational support across the different stages of that. And so as part of this, this is a slide that Kate prepared, that we've tried to think about the user experience, because we know that these things are episodic. So if I need to create experiments, you go here, that dashboard we mentioned, that's the choice you make. And in there, we know there's different series of tasks. You have to create it. You have to create your entry list. You have to create your design, assign your locations, and then review what you've done. And again, this will be metadata driven as we define, these are different programs, and these are different types of experiments, and these are controlled values. So when we work with a breeding program, we'll define them, And as you, getting back to this authentication logic, we will know who you are, therefore we will know these are the right choices here, so the interface is tuned to who you are and what you're doing. But to the minimum viable implementation concept, initially the logicals will be here, but we won't have done that yet because it's more important to expose this logic and have you be evaluating. So initially you'll just have to know what's the right choices to make. Another key part of this, getting back to the science, that as you go across the stages, you're winnowing out entries, but you want to be testing more locations. And you kind of have a spike of traits. So earlier on, you're just sort of trying to sort. These are ones that may work. These are ones that clearly won't. And so you want to have a few key selectable traits. And that, to me, is one thing that Matthew's working on with his and the physiologist. So what are some key traits that indicate successful behavior? So in some sense, you can then have a type of experiment that's really more a phenotyping assay. And so it's very efficient, high throughput, tuned to just making that selection. But then in the middle, you need to have a better understanding of G by E by M. And so you have it overloads your primary yield trials to collect all these other traits there. And so just tune them to the core traits that are for making that product acceptance decision. But you have to understand, well, what's driving my yield? What's driving my insect resistance? And so that's what these trials are for. And so they're kind of in this period. This is 1, this is 2, 3, 4. So in here you're going to have a lot more traits, but they'll be more associated to these. And then when you get out here more at the end, you're really just having your primary trials, and these tester traits are, this comes from a maze background, so it's your maybe check. That you want to have a widespread planning of checks across everything. Again, if you have a panel of 6 checks, that just means maybe 12 plots per location. But that's how over time you build up data to really understand the context and ask yourself in a given year, how representative is that year from other years. And just here's an example of a complex G by E by M, that I've got 3. My primary treatment level is as a stress concept, and then my secondary treatment level is a planting density concept. But then in order to force a sampling of field variation, I've got two replication blocks. And so it's just trying to highlight, and I'll come back to this, but these are the capabilities that we've identified patterns for experiment creation. That here's my experiment, here's my entry list, not only what they are, but they have roles. And then I need to choose a type of design and choose levels or elements of the design, and then that's just generic inputs to an appropriate set of statistical design modules. So we can do this in a very generic, scalable way, going forward. So seed inventory management, of course, that's also key. That is what you're working on, but also they have their own set of knowledge, and kind of as a cartoon here, that we'll have the concept of just what's the actual bag of seeds. And of course, anytime you make some of them, split some of them, make some of them, they'll have a unique identifier, and that points to not only where they are, but who, in some sense, owns them and how much of them there are and things like that. And seed inventory management functionality, of course, is the ability of you to ask, the answers to those questions. But we also have an identifier that captures the genetic concept it represents. And then we have the product concept that we think these are instances of. So a product concept could be associated to a particular breeding program. It says at this stage, I think this genetic concept may represent that, and here's its seed. And of course, you do that trial and you make a decision. They do or they do not. This genetic concept in seed could also go to some other breeding program because they may also think it has similar potentialities. But as you go along, you're just, making seeds for each of these stages. So of course, earlier on, there are new genetic concepts, new inventories, but in some sense, you have a coding or a fixation or classification, and then a genetic concept is fixed even though the seed inventory representing it may exist many times. And if there's some concept of commercialization or release, then it has, that identifier. So seed inventory has to, manage, these concepts. And just here's some screenshots Kate prepared. So one key ability is that ask, what are my seeds? Where are they? How much do I have? Other information about them. And this is key to experiment creation. You can create lists of that you can use then to say, okay, here's the ones I want to use as my entry list for breeding trials, or here's the ones I want to use as an entry list to a nursery crossing experiment or a seed increase experiment, or here's a list of things I need to send off to the genotyping lab for genotyping or seed health assessment. So this is an example of the seed inventory management functionality that will exist in B4R. And of course, it drills down to, well, yeah, it's sitting there, in that building, that room, that bag of seeds. And again, I don't want to, we were concerned about a live demo, so Kate took the time to make screenshots, but I don't want you to hear that, there's not something there. There is a real B4R there. There is real things there, but we're working to add appropriate functionality for maize wheat, to make it suitably generic to be crop agnostic, procedure agnostic. So there is there, but in terms of, I'll say the EBS B4R or the parts that assemble as an EBS, like we talked about earlier, that's the focal point of the work this year. So field implementation is key in several ways, that we've centralized in B4R the creation of experiments. This generates this array, if it's an array of plots, according to how many locations or places it's going to be. So if you have 5 locations, you have 5 arrays. If you have a particular statistical design, they have that pattern inside that location. So that's where you're generating them. And then we'll come to what we're, and this for us, so this is B4R, this is KDX, the ability to take that and map it to the piece of ground. Because when you create a design array, it's going to be perfectly uniform. But the ground may very well not be uniform. You have to have a jag here, or insert a gap here. You have to adjust it to the ground. And so that's the mapping activity. And that's where you get the actual, not only Cartesian XY coordinates of your plots, but also the concept of a geospatial object and geospatial coordinates. So that's where you inherit those coordinates. And of course those come back, but then this also illustrates, so we come to there, but this illustrates, here's where you start having an adoption activity, that the wheat program has their combines, maize program theirs, IITA has theirs. So we can provide this necessary input array to them, but the EBS team is not going to actually do the work of having the combine being able to consume that. But by so doing, they can give us back the data. So of course, we need to have the ability to receive that data. And so, we'll do the same with high throughput phenotyping and handhelds and planters. We will create seed inventory management functionality, but again, everyone has their own cold rooms. We're not responsible for their cold rooms or their gene bank facility. So this illustrates, how we're doing it, but it also illustrates, again, the starting point is here. This array can go here for, again, this mapping, planting. It comes back to here, but then this allows us to grab all of this data in a software-based fashion, for breeding trial analytics, because we've defined the array, we've connected it to appropriate coordinates. All data is collected, to that mapped array, so therefore we can feed it to there. But the other thing this illustrates is that this is centralized, this is online. You as a breeder go online, you create these things, you bring them down to here. This is your laptop. You can be totally disconnected from the internet. You could have a handheld, it's talking to this, again, totally disconnected, doing the work out there in the field. And when you've done that work, you can come back, plug in, and then you can upload the data to here, to do the analytics. So this is a key part of our strategy here. And then Kate took some screenshots. You have this concept of a field, and in there you've got areas you're going to plant, and you're taking your this design array and you're fitting it into there, and you may have to again adjust it in different ways before you inherit the actual coordinates. The other thing is you collect data. Since you're there in the field, you want to summarize that data. Well, also as part of experiment, a property of that is what traits you should collect, and also things like planting instructions and management instructions. So it comes to here so the people doing that work have that information, but also you want to be able to ask yourself, well, I was supposed to collect these traits, did I collect them? And also traits have a collection protocol. Do the values make any sense? Was there mistakes going on? So, there you are with the people you're working with in the field, so you want to do that work then and there. You don't want to have all this data uploaded back to the system to discover, there's all these different types of errors. And so that's another important part of this functionality. Kate's just illustrating some of the functionality that's there in this KDX. Well, a key part of this is then being able to analyze, that if you have a product profile, you have a stage, that stage has an objective, or it's testing, certain inferences. And so there's many different types of analysis, and we're going to focus on this one first and then extend to this one. But again, it's the same source data. We're just putting it together different ways to drive different things. We can all use the same compute resources. We can capture the outcomes, and they could feed back as inputs to other things, and we can integrate them not only by class but also across classes, so we could put things together for decision support. When you do an actual trial, it's obviously not, things bounce around. How do you understand what really happened? And that's where the ability to conduct all the necessary analytics then and there is so critical. And so because of that, it's very easy for what you think should have happened versus what actually happened, to not align, have these yield gaps. And so we're going to start with phenotypic analysis because it is what's the starting point for genomic selection. It's a starting point for understanding, your errors and predictability. It's a starting point for validation, training data sets for other things like modeling and machine learning and whatnot. So it is the critical starting point. And we'll generate BLUPs. I don't want to get too much into this, but this is the most appropriate value for defining what was the predictive outcome of a breeding trial. But of course, where BLUPs have shrinkage based on the error. So the more error is, the more the value shrinks. And so there is going to be some training education here. If people are used to using just adjusted means, they're not going to look necessarily like what the BLUPs are going to look like in terms of their values, but means that have poor predictability, BLUPs have high predictability. And also the other thing we want to do is you need many different types of analyses. You need your primary phenotypic inference, different types of G by E, by M, but also there's interactions between genetic concepts because we have a lot of concepts of testers and families and pedigrees and things like that. So we need to be able to understand that. And various interactions that help us understand repeatability and whatnot. So we need to run lots of different kinds of analyses. And so we'll boil all this down to the request interface for you, in effect, are choosing what was the data I want, what models do I want, and what's the purpose. I just want to get some data because I'm going to run this offline, it's exploratory. Or I'm going to want to capture errors in my traits. So there's different types of analyses There's different ways you can prepare traits. This is where you analyze each trait individually. This is where you're looking at the prediction based on multiple traits. This is how traits vary, the variation between them, and this is the genetic correlation between them. But also, when you have an array, you could have single experiment, single loc, up to a multi-experiment, multi-locs. You could go to, multi-year, multi-trial analyses. And you could ask, well, what are my types of inferences, that you want to capture, out of an experiment? And here's just an example, that very complex G/M experiment, that we can write models that capture all the interactions there, and from there we can capture all of those inferences from a single model. This is the overall phenotypic inference. This is the behavior of my location, or in that instance, this was my stress concept. This is my population concept. This is the interaction of my variety with the stress, variety with stress and population, variety with population, all three. And this is my error, control for, spatial adjustment. And so, we can use, and we'll use ASRML because it is the best tool for doing this type of analysis. And part of this, I mentioned the spatial adjustment, so there's many different types of errors that are in the field. And so we will apply row column adjustment and AR1 adjustment to capture that error. And you'll see, here's unadjusted, you'll see adjusted, well then this is the signal, this is a signal plus noise. And so we'll capture that. The other thing we'll enable is the ability to do a hierarchy. You want to look at, so in B4R is the ability to look at your traits and again capture any egregious errors, but also perhaps classify them in terms of the continuous, whatever, categorical. But then we can run an analysis to capture, outlier data points, run an analysis to capture outlier entries, run a data analysis, see if there's entry classes in there in case we need to partition their variances. We can look at different types of models. We can look at different types of location classification. So we can, it's the same software logic for doing all this. It's just different models. So in analysis request interface, you're just choosing, this is what I want to do. Here's the input data. Therefore, this is the right model. And we just run that, push the button, and it runs. Because that's key to those EIB objectives of breeding program modernization. So that's a main point of this. The other thing I want to mention is that, here's the covariance variance correlation matrix from a factor analytic ASRML analysis, and we're capturing this information. So again, I mentioned that not only are the outcomes per se critical, but if you want to understand or start developing other types of predictive analytics, this is key input to that. And it'll just look like this. This request is where you go and generate that. You're just defining data, model, how to prepare it. And so the things in green are 100% generic. And this is the different modules, so they just drop in there, and so they can take advantage of that. So I have used a strategy to implement well over 8,000 different models, so I know that this scales very well. But this will be a key adoption activity with your biometrics support, that for your product profile at this stage, what are your inferences, what therefore is the right model. But again, there's significant need to do different types of improvement analysis, discovery analysis, whatever, because this is production. You've defined the method. This is where you're learning the method, but we can still scale that by making it easy to get data, but also execute on data. And analytical sampling, we've honed in on, these 4 high-level use cases. And so this is an example of system behavior, that in the breeding system, you're generating requests for genotyping. If it's an actual, say, nursery crossing experiment, then of course this is the planting of it. So this request here, in the context of the vendor, you're going to use, the assay you're going to use. This is how you do sampling, how you organize shipments. It goes to analytical lab. If it's an analytical trait like seed health, that can come straight back. It, we'll accumulate, genotyping data in the GOBI database. But since we know what it was for in the association of experiment element to sample, we can pull data up directly, for germplasm classification, germplasm selection decisions, or into breeding trial analytics. And here's a cartoon of that. This is the phenotypic array. You have an experiment at 2 locations, 2 entries. Each has 2 plots, just 1 trait. I run the analysis, so now I've collapsed the trait to a BLUP. But then, since I've sampled these entries through that sampling workflow process, I can then associate marker data to the entry data, so I can by following this workflow and these system properties, very quickly generate genomic selection arrays. And I mentioned this is going to go in stages. So phase 1 is roughly, up here. Phase 2 will be here, because we are dependent on implementing, that sampling workflow. It's not only the EBS team effort, but we have to then, coordinate that with work that the GOBI team is doing. And in decision support, we can capture these outcomes. If you've looked at this happens to be an example of looking at insect resistance. And so you could have had an assay to measure protein expression of the gene producing the insect resistance protein. You could have had an experiment looking at the resistance to the insects themselves. And you could have had an experiment measuring yield. But then there's different interactions between them, so you could understand, biology tends to be a zero-sum game. If you push it this way, you're diminishing over there. So what are your acceptable interactions? And you can put all these into some type of decision-making, format. And then I think I want to mention a little bit, and I'll come to a close here, that within the EBS, again, you have B4R is creating experiments. We can capture outcomes, from executing on those experiments, in breeding. So this database, though, can be exposed to external things. If this was oriented to a wheat use case, if your international nursery partner needs an array, experiment array, they can get it. If they want to give us back data, they can get it, because we're doing these APIs anyway within the system to communicate between parts of the system. But if they want, like a lot of what Kate works on with publishing the data to germinate and whatever, they can come here and get that data. I want to touch on data migration. That is one of the most difficult things for us to solve, given that we're coming from much simpler systems where many data model concepts were not formally defined, but also those systems didn't necessarily have referential integrity. They didn't enforce certain ways of doing things. It was up to the breeding programs to make sure they themselves did it the right way, but of course that always shifts over time. And so the data is not well formed. And so we have to map it to these concepts, because without that, we can't enable, these software operations that we've been describing. And so, Kate is then our lead on this, and this is her slide, and she's working on, what are the different, phases. We've mentioned different types of metadata and whatnot to drive software, but also we've focused on what is, the germplasm, because that's what's necessary to the metadata in a germplasm is necessary for a breeder to start using B4R to, start using the software functionality. And this is a team involved. Since it is a serious effort, this is a good 2 days a week of Kate's time, and we greatly appreciate that. But also we have the head of our data model team, Arjun. Here we have Erica, who's also very involved in the data models, database logic, whatnot. We have Newman, who's responsible for the ETL logic to take data from, say, IWAS to B4R. And we have Jorge, who's responsible for those APIs. And of course, to actually deploy it, because part of deployment is when we get a release from B4R, we have to load our data to it. And that's Jay. So given the seriousness of this effort and the importance of this effort, we've defined a practice for doing this based on professional standards, and we set up a team for doing this. And anyway, I think and so let's just end here. And so this is our key deliverables. It was important to get the steering team going and, get the IT team going, to define and execute our practices. Work with the Gobi team to start working jointly on this genotyping, workflow. This is something that's going to be more the end of the year, but we have to start anticipating what has to happen for not only ourselves to adopt this software in 2020, but these other programs to adopt it in 2021. And this will be an area that we'll start collaborating with the IBP project, because they have a very experienced staff on site to help us do this. So we want to start defining with key stakeholders from not only ourselves but these other institutions that this model and what we must do, and define then activities for next year and beyond, and who's going to do what and how. We have to start more formally bringing in Module 1 and Module 3 genotyping concepts into that. So we're starting a group with the Module 1 lead, the Module 2 lead, the biostatistics group here, some key breeders such as Ravi. And we have a collaboration point with Corteva, their statistics group, to more formally define these concepts, schema, not only scientifically or statistically, but also informatically, so we could start implement them. And we're going to start a project here, I'll say in July. We'll have a B4R IT team member start working on software for breeders to define these things, so that this metadata we're talking about can become available to software. And we do need to have connection points to big data, because it's through them that we tend to connect to seed systems and things like that. And of course, raising money. So we've been asked by the Gates Foundation to write an extension grant for the Excellence in Breeding that funds this project. So we've prepared that. So anyway, that's where I'll stop, because we wanted to end it at an hour. And we have other slides in here if we want to talk more, or anyway, I think this is supposed to go an hour and a half. So we wanted to leave sufficient time for questions rather than just spend all this time talking at you. And I just want to say Kate is very important to this work, because from the data management effort leading up to this and this transition to this and her work in this, and so she did help prepare and vet and review these slides, but she asked if I could be the talking head. So anyway, I just don't want it to not, I want to make sure Kate's role in this is acknowledged, along with the other members of the EBS team. And I'll point out that Marco here from who heads the IRRI, part of that EBS team, is responsible for BFAR, is here. I don't see Ernesto, but other members of the EBS team are here. Anyway, I don't see Ernesto. Jay is here, DevOps. Victor, Analytics. So many of the key team leads are here. Anyway, that's where I'll stop.
Can
Yes.
don't know if this is a fair question to ask, but what is your ultimate measure of success?
No, that's
In this case, is it, because I noticed, I did that recently, we wrote a little commentary last year, and I was struck that the genetic gain in wheat has been constant for the last 40 years, almost at 40 kilograms per hectare per year. So do you have something like that in mind, that you're going to measure your success by breaking that barrier from 40 kilograms to, let's say, 50 or 60 kilograms per year per hectare?
Well, let me, that means I stopped on time. Let me step back from that. You know, that's a very important question, and certainly both at the EIB level and these different, you know, grants were prepared, you know, we have to try to define that. So from an EIB perspective, that a breeding program has a, I'll say, suitably defined product profile, not only in terms of what its characteristics are, but that's also a concept of the target product environment that the breeder is working in and how that maps to the concept of a market segment. You know, so if that's not defined, how can you measure? And it, of course, would have a definition of success, usually is compared to some comparator. So if that's not defined, how do we know if we're making any progress or not? The next step from that is, well, what's my breeding schema? There has to be the concept of a stage, and a stage has an objective, and therefore does it have an appropriate design in the sense of choice of germplasm, you know, statistical design, choice of locations, traits. And so we know that there are practices necessary, practices of a certain caliber or purposefulness to get to genetic gain. And so we'll start with the starting metrics are those practices being defined and adopted? And more specific for us, are we delivering the IT capacity to execute those practices? And so a little bit more formally for us, do we have appropriate IT functionality? Are breeders actually using it correctly? And by so doing, then these are the best results defining the outcomes of these trials, and that's how we're going to ask ourselves, are we improving selection, accuracy, and
No, I don't know, I understand you're getting into this
that
process.
It has to be broken down into very
Yeah,
much
you're
like
getting into
that.
the process again. I'm saying that there is the process part that your
Yeah.
seminar was based on entirely, almost.
Yeah.
All those algorithmic kind of like flow charts, and they were beautiful. I mean, I'm sure they were very clear to you. I am trying to get to this difference between the process and the result.
Right.
So for a result-oriented person, how do you define your success? I mean, you are still kind of like involved in that process, whether breeders do this or not. What I noticed from your teams, that breeders are sitting on the edge. They have allocated 1 or 2 people to work with you to compare whether what you provide is going to beat or exceed what they do, or if it's going to be the same that what they have been doing for decades. So how do you, let me put the question around. What's the timeline? When can you see success? Is it 5 years, 10 years, 3 years?
Well, our timeline for, again, this, in terms of just the IT, it's just the core minimum viable implementation this year. Next year, what are the necessary enhancements to start having more systematic adoption by CIMMYT, maize, and wheat, and that, of course, will continue into 2021. And so it's going to take us a good 3 years to get to where the system is fully formed for their needs and the appropriate, you know, trainings and whatever, you know, to be using the software have happened. And so that's our timeline. And of course, in terms of just adoption metrics or, you know, qualities of software metrics, you know, those will be our core metrics. But again, that has to be coupled to the breeding program improvement things that they're doing with excellence in breeding. And, you know, we can't, you know, obviously at this point we think that if they adopt these practices and we deliver the ability to execute them, that will lead to these improvements, but we won't know for sure, obviously, until a couple of years down the road from applying these practices and having the outcomes of them. But a key then feature of this is why these operations are happening in system is that we'll be capturing that data that's necessary to ask, what is the adoption rate? What are the qualities of trials versus the outcomes of trials? Where is error? That's how you try to understand why you're not attaining a specific
So I see
product objective or not.
I see 5 to 10 years sort of like time horizon than this, because
Well,
the initial phase is going to be like this evaluation by the breeders.
Yeah.
So you have 3
Well-
breeders from wheat, and you have 2 or 3 from maize. And the majority of the breeders are doing what they have been doing. So they will evaluate 3 to 5 years from now whether it adds value, and then they will probably adopt or not adopt.
Well, it was intentional on Prasanna and Hans' part that we just start with a smaller number of breeders since we're getting started. As you get to where you're working for more systematic adoption starting next year, that circle of breeders has to expand. But again, from my experience, it takes a couple of years to have more complete adoption. And Julian, you've been working with breeding programs. That's one of the things you focus on. I mean, I think we have to be realistic that it takes. You start with those breeders who are vested in this, and you get the process going, and you expand the circle through a series of hops. And also, as you know, breeding is continuous improvements. You better design it to be that you're learning as much as possible from each trial to understand how to get better, because without that, we'll never get the genetic gain. Yes?
Thanks, Tom. The descriptions you showed look very complicated to me, and I just want to ask, will this breeding system tool be useful for me if I don't use product profiles and I only have 2 stages, not 5, or I have 8 stages, not 5? Or is it going to straitjacket me into using one system that EIB or somebody else thought is the best way?
The answer is it will not. You have to allow people to do an activity like create a trial. Whether that trial is been optimized in different ways or not, if it's a more formal, product profile trial, or if it's just some basic observational or agronomy trial, whatever, it's the same software logic. It's how you're using the software that different. What the purpose of the trial you've created. That's what different. It's not software logic. It's the purpose of what you've created. So we have to enable current or basic or heterogeneous operations. For instance, I'm a Genebank person. I need to create trials and plant Genebank holdings for different, data gathering activities. So that's no different than a formal, phase 3 product profile, yield advancement trial. The software logic is the same.
More questions, concerns? Okay. My friend?
Bueno, when you show the slide for the migration for the data, I couldn't see in some of the steps how you will validate, like when you migrate the information, like we have in different platforms and different data models. Now we will get the same results with this new data model.
Yeah, so that's where it is a difficult process. So I don't know, Kate. You're running the process. If you would like to speak to that, otherwise I can give my answer to that. So that's where this first one is. We have to define with the person who is a current steward of the data a representative use case. And then we have to do what's called a source to target. It's pretty specific, you know, that in your source, whether it's a spreadsheet or a database, in some sense, table column maps, you know, to target table column. But there can be, you know, data definitions. You know, here it's if it's a string, you know, then it needs to be a string. You know, can it be nullable or not? You know, there's relationships that have to be mapped. There's various constraints such as not only besides data types, but also there may be some metadata that's important. So you have to, you know, do that mapping, and we have to agree with the current steward that we think that's correct. Now, once we've done that on the target side, we may realize that, yeah, it just goes in, or no, you know, there's a mismatch there, and we may have to clarify data models to handle that correctly. We may have to do some software development on the target side to, you know, to add a column or something to a database. And then you have to define what you call your extract, transfer, and load. It takes the data from where it is to where it should be according to these agreed upon rules. And as part of that, there may be transformations, because in the source system you called it X, but now in the new system we've agreed it's now called Y. And as you do that, it will throw out exceptions. Well, first of all, for what does migrate, that use case then serves as the ability to test. Do I agree that the outcomes are what they should be? And that test is both programmatic, but there's what's also called user acceptance testing, where you agree, you look at it and you say, yeah, I agree to this. But also the ETL logic is going to throw out exceptions. And then, because there's always irregularities in data that we, you know, since you just start off with a use case, but you applied it to all the data, you're going to trap irregularities. And so how do you handle those? And so my experience is that a complex data migration could easily take 6 months and take several hops. That's why we've invested in defining this practice that I talked about and have created this team for doing it. So, because I agree with you, it's challenging, and but also along the way we may make some pragmatic decisions that, well, is this data really useful anymore? You know, don't invest in it if it's not useful. And so we have to prioritize. But anyway, data migration, part of the reason we're investing in this, there's always data migration. It's an ongoing effort in IT, whether, you know, for us, since we haven't had systems bringing things into the systems, but as systems evolve and progress, you know, you have to manage change within the system. And so anyway, I agree with you. It's a complex effort, but that's why, again, we've invested in the practices and team for doing that work. And we're going to start focused on, I say, just maize, wheat, germplasm, because that's the essential starting point. You know, the concept of, other than if it's necessary to define germplasm, the concept of a cross or trial, you know, we're not going to try to bring in experiments per se. And maybe, you know, it's all germplasm. Again, that may occur in phases because there's different definitions of germplasm per se, you know, such as just core GMS definition versus, you know, more comprehensive definition. So quite likely even that will be in phases. But again, that's something that, you know, we have to agree on those things, because, you know, and that's starting with this breeding advisory team. As Karen Walpole mentioned, they're just the tip of the iceberg. You know, they, in some sense, at the starting point, represent their programs, are a contact point to those programs. As we get into more specific activities, who else do we need to talk to? Because, you know, the wheat program is not just those 3 people, and it's not just breeders. You know, there's many people who are in our breeding program doing different things. And so they're just sort of to help us make decisions, higher level decisions about what our core objectives, who really needs to be involved. This is the actual project. When it comes to the project, they will help bring in more people from the breeding program, but also we'll bring in appropriate people from the IT side, you know, to do this work. And I don't want to, I've been here about a year. I know CIMMYT's struggled with this a lot, but it takes, a serious effort And so I think, that if there's one, I think we're trying to do that based on our professional opinion of what it takes. That's why we formed this team, that's why we've established these practices, not only IT practices, but how we work with breeding programs, both more tactically but more strategically. And again, none of this existed a year ago. This is, certainly we can all draw on our experiences, but none of this existed a year ago. So we're in year one. And I will say that, we start, the core team initially was a B4R team. They delivered what we said they would ask them to deliver when it was supposed to be delivered. So we've demonstrated the ability to do this. And now that we've expanded the team, of course, there's always some scaling up lessons learned, but we have scaled up, and on the whole, at this greater scale, we did deliver. And getting back to data migration, Kate worked very closely with the data modelers and the ETL people to say, for this use case, what's the right practice? How do we actually capture these mappings and rules and logic? And how do we test that? So we've been doing that. We've done the goal for June for data migration I think we ended up with a maze use case, do an end-to-end execution of that process. And we did do that. And again, it wasn't perfect because this is the first time we've done it. But, we're adapting to that, and we'll then continue. And I think the first goal is to have the GMS tables populated. I don't think we have an exact, but I would say that will be a key deliverable for July, is to populate the GMS tables. Tara, you're the product owner. Do you have anything to add?
Is it already on? Okay, so to address what Kanwapal was asking about, I think success for me as a breeder is actually a lot simpler. I mean, right now we really don't have any tools other than Excel and a few macros and a few other programs to do our work, and none of them are connected in an integrated way. This makes anybody, it doesn't have to be a breeder, anyone in this room doing any scientific research in the field or in the lab for that matter will tell you that this leads to a lot of wasted hours, which is a lot of wasted money, obviously. So whether you're Sarah Hearn pulling down genotypes that basically blow up her computer because there's so many data points and Excel can't handle it, or if it's myself trying to do ASREML analysis on some pretty complex drought trials, we waste a lot of time not actually doing the science, but just doing the prep work, and hours and hours just doing the prep work and trying to get the files in order and making sure there's no mistakes, etc. So really, success for me is defined by an integrated system that in its first iteration is probably quite simple, but at least allows us to do alpha to omega in the breeding cycle, whether you're more of a field breeder like myself or molecularly focused as in Sarah. And then within a relatively short period of time, let's say within 2 years, so by 2021, that we actually have this integrated system and some fairly sophisticated ways of working, whether that's creating trials or genotype jobs, and then being able to gather that data together with ease and rapidly, and then to analyze it with ease and rapidly, and then also to be able to display those results in a let's say a user-friendly way for presentations or whatever. Then, to address what Kevin said, Kevin, really a lot of that constraints or whatever is really about you and leadership.
in terms of CIMMYT, I mean, I think that Tom has explained pretty well how what do you use? Agnostic is the term. In terms, EBS is agnostic, but then each institution will have to decide. So if we're talking about stage gate advancement systems and things like that, we're tied into, and Tom also mentioned that, we're tied into the EIB. So leadership at CIMMYT is going to have a lot to say about how flexible or not flexible this system is for the CIMMYT user. You won't be able to say what's going on at IRRI or IITA or whatever, but at least for CIMMYT. And so I think that, at least the way I envision it, and I know Tom agrees, the way we envision this system is that each institution will put in as much structure or as little structure as they want. But I assume that, anybody who's participating in EIB, it's not going to be the Wild West that it has been at CIMMYT for 50 years. There's going to be a lot more structure and a lot more limitations as to what, at least in the MAZE program, I think the expectation will be that you are following this stage gate system, and to advance from one stage to another, you have to show data that the products advancing do meet the criteria, et cetera, et cetera. So I probably there will be a lot of restrictions. I put that in quotes. For me, it's pretty normal coming from the private sector. I think the Institute has a right and a duty to make sure people are following certain protocols and in their decision processes. So
And
that's
this
it.
slide, to reiterate what Terry said, that with Terry and in our steering team, the heads of the reading programs, excellence in reading, these early adopting readers, we have to do basic trial operations, so that's the starting point. That's why that's what this list captures. But we want to be, since we are working over time to build a more comprehensive system, in parallel, we're saying, well, here's the right overall data models, here's the right overall technical architecture. So we'll build these things to those models, to that architecture. But again, the initial functionality is just going to be basic. Focus on this, not only to ask, do we get it right, with not only in terms of software logic, but readers. And then from this, we'll build in subsequent phases, ultimately to more sophisticated features. But in some sense, it never ends, because reading evolves and you need to add new analytics. But that's also why we're trying to think of it as a system. It's modular, so that if you need to update something, you can. It doesn't blow up the whole system. If you need to, refactor something, that, again, it's generic crop agnostic, procedure agnostic logic, so that it gives us that foundation of flexibility to go forward. Anyway, so that's where this list came from. A breeder should be able to, starting next year, do these things with our software. But again, Carmel, to your point that not all breeders, I know some won't want to, and some will really want to, and some will be in between. So it always takes, a couple of years. Yeah. Yeah.
Okay, more questions, comments, no, doubts, complaints? Okay. So, anything else?
No.
No.
Well, thank you, everyone.
Thank you. So there's a copy over there.